Okay, let's begin. This video's topic is again standard additions. This is actually the second video of relevance to standard additions. The first video considers a single point approach, and this video is going to consider a multiple point approach. If you have not watched the other video, I would recommend that you do that first and then return to this video. This topic is pretty important. It's got a 3.5 out of 4 star importance. And it's pretty likely you're going to encounter something like this along the way in your analytical chemistry class, okay? So again, what is standard additions? It's a form of internal calibration. We're going to run our calibration inside of the actual sample. We do that by spiking the sample with known amounts of analyte and then analyzing it. We do this when the sample matrix is complex or unknown. Again, this word sample matrix, or this phrase sample matrix, is important to you. What that is everything else in the sample except for the analyte. The reason why the sample matrix is important is because other substances in the sample matrix can affect our sensitivity of the analysis. And if we use external calibration to run our quantitation, it's pretty likely that the result might be inaccurate. Because if the sensitivity changes, remember that's the slope of the detector response function as a function of analyte concentration. If that slope changes, the external calibrants are not going to accurately reflect the situation within the matrix. So we're going to use standard additions for such cases because they can eliminate this matrix effect. Now the other video considered a case in which we did a single point addition. That was the first way you could do a standard additions analysis. Only one spike, but this video is going to consider the second case, which you could argue is going to be better, more precise, more accurate. And the reason why is because we're going to do a multiple point analysis. Instead of just spiking our solution once, we're going to spike it multiple times. And as a consequence of doing that, we're going to improve our precision. So to explain how this works practically, let's consider this middle section of the slide, and I'll basically talk us through this and then go through this equation at the bottom, which is going to be crucial for the quantitation. If we're going to do multiple point standard additions, the way that we carry that out, or a way we can carry that out, is we'll take our original sample. This is what we want to know, the concentration of the analyte within, and we're going to subject it to our analysis. We're going to record the response of the instrument that we're using. Maybe it's a spectrophotometer, ion selective electrode, chromatograph, whatever it is. We're going to measure the original sample first and record the response. Okay. Now we don't know what that is, what that means yet, because it's just some absorbance unit or voltage or something of the sort. We need to calibrate and figure out what this number means in terms of the concentration of the analyte. And that's our problem. We don't know the sensitivity. We're going to figure out the analytical sensitivity within the sample matrix. And the way that we do that is we add a spike into the original sample. So this same sample, we're going to spike in material. Now what is this spike? The spike is going to be the analyte. We're going to purposely add in some more analyte into the sample, thereby increasing its concentration. So when we analyze the spiked sample, the detector response should increase. Here it was 0.614, over here it's 0.817, okay? That's just reflective of the increase in the detector signal because we've added spike. We've added more analyte. The signal should go up if the detector is working properly, okay? Now what's different about this multiple point approach from what we talked about in the other video is after we do this process, we're simply going to do it more times. Okay? We're going to repeat the spike step and measure the detector response n more times. Maybe it's 2 more times, 3, 4, 5 more times. Okay? The purpose of doing it more times, as we'll soon see, is instead of just getting or deriving the analytical sensitivity between these 2 points, that is the slope of the internal calibration line between these 2 points, instead of doing that, that's the single point thing. If we repeat this process more times, I'm going to have more and more points to use to extract the sensitivity or the slope of our calibration line. That's a nice thing, okay? And the reason why is because If either of these 2 points are a little bit in error, that's going to sort of maximize the error of our slope, which is going to ultimately lead to the biggest error in the quantitation of our analyte in the original sample. But if I repeat this process 3, 4, 5 times, and I derive my slope from my best fit line through all of these points, all of these spike points, that's going to probably yield a more accurate slope. And as a result of that, I should be able to extract out a more accurate analyte concentration in my original sample. So the big difference here is we're going to repeat the spike and measurement process 3, 4, 5 times instead of just doing it once. And that's what I mean by multiple point analysis for standard additions. Now, on to the mathematics. The key equation for doing multiple point standard additions shown down here at the bottom of this slide. I highlighted it in red to denote its importance. Okay, it's actually a linear function that will be crucial to us here in a second. Now, to define the variables, they are the same as those that I used in the other video, if you've already watched that, but just to mention what they all are. These S terms, you'll find one here, here, and up here. Not this one, okay, but this one, the S sub S, and S plus X. Those are going to be the signals that our detector responds. The S sub S is our original signal from the original sample. So here that would be this 0.614, okay? This one, the S with the S plus X as a subscript, is our detector response for the spiked samples. So the first spike produced this, 0.817, as this number. We don't have the data for the other spikes, but that would be what that is, okay, what that corresponds to. Now the V's are always volume terms, There's 3 different volume terms that appear in this equation, okay? There's V sub 0, that's our original volume. There's just V, that's V total, okay, so that's the total volume, the original sample plus whatever you spike in, the total spike amount, okay? And V sub S here is the volume of the spike, okay? So I could write, if I wanted to here at the bottom, V sub S plus V0 is equal to V total, okay? You're confused by that, but that's what our 3 volumes correspond to, okay? And there are 2 other numbers that we should talk about then, or 2 other variables. This S in square brackets sub I, that's the concentration of the solution that I'm going to spike into my sample. So I said I added a spike. You usually do that by adding a certain number of milliliters of an aqueous solution or dissolved in some solvent. You know the concentration of your analyte because you make it a standard solution, you make it to a very precise concentration. You need to know that concentration. That goes here. And then the only other variable I see here is the X in the square brackets with the I. Well, guess what that is? That's the concentration of the analyte in the original sample. Okay, so that's going to be our unknown in this equation. Now the key to this equation, as it turns out, is it's a line. And I've tried to show you that by writing the y equals mx plus b form of the line up here at the top. Okay, our y variable is this product. The product of this volume ratio times the s, the subscript s plus x. Our b, which is our intercept, is this, the s sub s. That's the signal produced by the original sample. Again, here that'd be this 0.614. The slope of the line is this ratio, which is s sub s divided by x sub I. That's basically the original concentration, or the original signal, excuse me, produced by the original sample divided by the concentration in the original sample. Then we've got their x variable, which is also a product out here. It's this volume ratio, Vs, the volume of the spike divided by the original, times the concentration of the spiked solution. Okay? So what our strategy is going to be, if we're ever faced with a multiple point calibration, internal calibration, this method of standard additions as it's called, is we're going to use this equation and we're going to make a graph, an XY plot. You can do that in a graphing program. I'll show that here in a second. But the strategy is going to be that our x variable is going to be this product that we're going to graph. The corresponding y variable is going to be this product. We're going to make a graph. We're going to find the slope of that best fit line that goes through our x and y points. We can find the intersect. And from the slope, we're going to be able to extract out the concentration of our analyte, x sub I. So that's going to be our approach. Let's see how this is done practically, okay? So I've made up a sample problem to help us here with this video. I'm going to zoom in a little bit so you can see it perhaps a little bit better. Now, if you're faced with a problem like this, you're going to basically be given a data table, or if you have to do this in lab, you're going to have the ability to collect a table full of data. And to not distract you, I guess I can more or less cover up this information from now. It's something that we have to compute later. But the information that you would know would be the original sample volume, that volume of the original sample that you analyzed. You would also know the molarity, or the concentration, of the analyte in the solution that you're going to use for spiking. Okay? So remember I said you're going to make a standard solution. Well, guess what? You're going to weigh out carefully the analyte that you use. You're going to know what volume you dissolve it in, so you're going to know its concentration. So in this sample problem, I'm going to basically just say that we have a 150 milliliter sample, and the spiking solution is going to be 0.56 molar. Other things that you will know are shown here in these two columns. So this is all data, experimental data that you'd collect in the lab or you'd be given in the problem. Okay. What these two columns represent: the volume of the spike solution added. This is the volume in milliliters of that solution that you're going to add for each spike, and the corresponding detector signal that was registered. Okay. So the first bit of information is 0 spike added. So this is none of the spikes. So this is just the sample itself was analyzed here. The detector signal was 0.712 units, whatever that is. Okay. Then we spike with 0.15 milliliters of this solution, that's 0.56 molar. Of course our signal goes up because we've added more. We increase the total spike volume to 0.75. Now our detector signal is this. This is the total spike volume as well, okay? Not the additional spike, but the total spike. We increase to 1.2. Our detector signal goes to this, and so on, all the way through almost 3.5 milliliters, which produces our maximum detector signal. So this is all experimental data. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8 spiked solutions along with the original. This is actually quite a bit of spikes. Sometimes there's only 3 or 4, okay? But here we've done a very comprehensive job. Now the question is how do we go from the sample volume, the analyte molarity for the spike solution, volume of the spike solution, and detector signals, how do we go from that information into a concentration of our unknown analyte? Okay? Well, we do that by remembering the key variables in our equation. Remember we said we wanted to make a line through our data? To do that, you need to generate x variables and you need to generate y variables. Now since this involves some computations and calculations, I like to do this in a spreadsheet, and that's what I've done on that data page, okay? But all I want to remind you or communicate with you what I'm doing here, because it's really pretty easy. You just have to kind of understand what's going on. To make my x value to plot, I'm going to multiply this concentration, the initial concentration of my standard, the analyte in my standard. This is the spike solution. And I'm going to multiply it by this volume ratio, the volume of the spike divided by the initial volume. That's going to be my x variable. Likewise, to generate y coordinates, I'm going to multiply my signal observed for each solution by this ratio of volumes. That is the total volume to the initial. Okay. So you can see what I've done then in these two columns over here on the right. is I've generated X and Y coordinates from this data just by multiplication. I've done this in Excel before I recorded this video, just in the interest of time, but all I did is I entered a formula in these two columns. I entered the formula for the y-axis, which was the signal, which was these numbers right here. So these are my S values with the subscript S plus X. Okay, that's right here. And I multiplied that by V over V0, where V is the total volume, which would be the 150 plus whatever I add, divided by V0, which is always just the 150. Okay? So you can see these numbers have increased ever so slightly, and that's consistent with what I just described, okay? Because the total volume will be just a little bit over the 150, except for the first case where it is 150, and then these numbers are the same. That's where we have not added a spike yet. Okay? So you can see how I generated this. This is sometimes called the corrected signal. It's what the signal should be if the sample wasn't diluted, basically, and that's what this volume ratio accounts for. I've done a very similar thing for my X coordinate over here, except I used my X variable from that other equation. The volume ratio here was the volume of the spike divided by the initial volume times the concentration of the analyte in the spike solution, which of course here is always 0.56 moles per liter. So I multiply the 0.56 moles per liter, because that's my concentration, times this volume ratio, which is the volume of the spike, divided by V0, which is my 150. So notice that these numbers all get really, really small pretty quickly, because this is a pretty small number that I'm multiplying by the 0.56. Okay, so that's where these numbers come from. There's not really a magic to it. I just entered a formula, copied and pasted it down the column, used these data points to generate these numbers. Now this is my X and my Y variable. I can take those numbers and I can make a plot on a Cartesian coordinate system that looks like this. Again, my X is this product of this volume ratio and my initial concentration in my spike solution. My Y is that corrected signal. It's the signal that was observed times this dilution ratio of volumes. Okay? I can then, after I plot all of my points in my data set, add a line through, it's a best fit line, through the linear least squares process. There's another video on that. I didn't do that here. I just use Excel, but it uses those same equations, that same approach. And that process yields this equation of a line in y equals mx plus b form. Here, of course, my slope is my 128.8, and this 0.7475 is my b. It's my y-intercept, which is right about here, okay? Now, why is this significant? Well, it's very significant for this standard additions. The reason why is because if you look all the way back to that initial equation, what was m by slope equal to? Wasn't it equal to s, subscript s, divided by x sub I? Well, think about what those terms are for a second, okay? The s with the subscript s. Wasn't that the signal from the sample that was not spiked, that original sample's signal? Here it was this, okay? This is not the number that we use in the example, but it's the detector signal for that original sample. And if I divide that by my analyte concentration in that original sample, that's m. So the beauty of this is I can set this ratio equal to m, my slope. And that's what I've done up here in the top corner. That ratio is my slope. Now the good thing about that is I know from my data pool what my original sample produced as a signal. I can look back in my data pool. When zero spike was present, that's my original sample, my detector signal was 0.712. So I can plug that in for my S with the subscript of S, because that's what that variable is, that original signal. And if I divide that by x sub I, I need to get this 128.8, my m, my slope. Now what is this x sub I? Well, that's my concentration in the original sample. That's what I need to know. And we're pretty happy now, if we're familiar with algebra, right? Because we got one equation with one unknown, we can rearrange and solve that. And of course, the way we do that is multiply both sides by the x sub I term. Which would yield this equation. And in one last step, I could rearrange that to solve for x sub I. And of course that's our whole goal here, because that's the analyte concentration in the original sample. And if I do that, notice my answer is, I had that on the other page, so I'm just thumbing to that so I can see what it was. I'll stop writing sig figs there. I haven't paid much attention to sig figs in this sample problem. I was just kind of getting us through all this, okay? So the beauty of this is my x sub I when I solve this. It's about 5.53 millimoles per liter, or 0.005527 moles per liter. The answer here is going to have the same units of measure as what we used for the concentration for the spiking solution. Okay, so here we use molar, so our answer is also in molar. It will be the same unit of measure. Okay? So this is the graphical procedure to find the concentration in the unknown. Again, the beautiful thing about this is we're fixing our slope here by all of these points. They all count to help us determine that slope. And hopefully that will lead to a more precise concentration than if we just use these 2 points. Right? Because that's what you're doing in the single point analysis. You're throwing away all this and you're just using these 2 to find your slope. Well, if you use all these other points, hopefully you get a better slope, and that leads to a better answer. Another thing I've always wanted to point out to students about this type of plot, once you make this plot, if you're worried about this math being correct, I mean, it's pretty straightforward, okay? But if you're worried about it being correct, another thing that you can do to double check it, go to find your x-intercept. That x-intercept, you take the, if you multiply it by -1 basically, is supposed to be what the concentration is. So I can kind of just double check and just make sure that's okay. Well, it's almost -0.006. So yeah, this makes a lot of sense, okay? So that is the analyte concentration in my unknown. So the key idea is here, it's a graphical procedure. We use multiple points to find the slope. That slope is essentially the analytical sensitivity within our sample's matrix. And that's all we're doing here. We're spiking and measuring the response, spiking and measuring the response, so that we know what that analytical sensitivity is. We know that relationship between the signal and the increase in concentration. And we use that relationship to figure out, in this calculation, what concentration of substance must have been present to produce the signal that we observed. So it's calibration within the matrix. That's all this standard additions is. The mathematics looks a little bit more complex than external calibration, but it really need not be thought of in that way. The key to be able to do this, again, is this equation that we already talked about, recognizing that it's equation of an align, knowing what the volumes are, knowing the S terms are the signals, knowing that this is your unknown variable right here. Again, the symbols here are the same as what they were in the previous video. So if you watch that, same symbols here, okay? And another thing that you really should remember about this is why you would want to do this. You want to do this process to deal with matrix effects. If you have a complicated sample, a complicated matrix, oftentimes you want to calibrate this way, okay? Because you gain confidence that your result is correct because you deal with these so-called matrix effects. And what that is, again, is just changing the sensitivity of the method due to something that's in your sample. That's what a matrix effect is basically defined as, okay? Things that need to be true for this to work. Detector response must be linear with concentration. and the detector should read 0 if no analyte is present. Okay, those are the two things that we need to have happen. We can see why that's the case. If this was a non-linear plot, this leveled off or something, this would not work. All right, we'd get a really weird slope. Another good thing about making the graph with multiple points is you can prove to yourself that this plot is in fact linear, a linear response function. If you just do the one-point calibration in standard editions, you don't have sufficient data to make that claim. Okay, so by doing multiple points, we can prove it's linear. It's another advantage of the multi-point standard editions method. That said, I hope you'd enjoy this video. It is kind of an important concept for analytical chemists, so I would rank it a pretty high significance. You're likely to see something like this in either lab or your lecture component. Thank you.